Hey, I'm going to be talking about arithmetic and prime numbers. And a quick review from our previous session. Last time we talked about numbers in different bases. And just as a quick review, the typical number is in base 10. This means that the digits that we use to represent a number are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 would be kind of like the largest that we're allowed to use. Let me kind of like move it a little bit there. So an example of this is the number 2,359. That means that we have two 1,000s, 300s, 5 tens, and 1 9. So in a way, we can represent this number as an expansion of powers of 10 because it's base 10. And the numbers that that we use, what we call the digits, this is what you get next to the powers. So in this video, I'm going to be using a lot of these for other bases. An example would be base 2. Base 2 digits, this is, for example, 0 and 1. And the place values, this is all of the powers of 2. So notice that we start on the right, we call that the place of the ones, and then 2 to the power 1, which is 2, 2 squared, which is 4, 8, 16s, and 32s. For example, if I want to write the number 10, the regular typical number 10 in base 2, which we also call binary, remember that what you need to do is identify the largest place value that fits into 10. That would be 8 because 16 actually is bigger. So the largest place value is 8. And if it's 1 and then the remainder is 2, use that remainder and divide by the next place value, which is 4. 2 divided by 4, that's just 0 because 4 is actually bigger. So grab that remainder and divide it by the next place value, which is 2. And 2 actually fits into 2, 1. And when the remainder now, it's going to be 0. And you continue dividing until the last place, which let's say the last one to the right, this is going to be the place of the ones. And since I have a 0, if you divide 0 by 1, that's just going to be 0. And the remainder is 0. But we need all of the divisions because then the number 10, you can write it using the coefficients, which are the numbers on the top. So 10 in binary is equivalent to 1, 0, 0. Now, this may seem surprising, but it's pretty easy to read. If you practice, you'll realize, for example, that we know that this is the place of the ones, this is the place of the 2s, 4s, and 8. So basically, you're creating the number by doing a sum. So here, 10 is equal to 8 plus 2, which is why you have ones in these places, because 1, 8, and 1, 2 actually forms 10. Okay, so then we are ready to start today's topic. So what I'm going to do actually is I'm going to focus on doing arithmetic, which is these are like operations in different bases, like sums, subtractions, multiplications, divisions. So example 1, it says find the sum of this number, which is in binary. I cannot read it as 11,000. It only makes sense to call it 11,000 when you're in base 10. But I'm just going to call it 11001 base 2. So add this number plus this number, both of them in base 2. One procedure would be to convert this back into regular base, into base 10, do the sum, and then put it back into base 2. But you can actually do these operations without having to do that much conversion. And it is pretty useful to learn this because it explains how the rules for adding, subtracting, and multiplying work. Basically, if you know how to multiply in base 10 and you analyze those rules, you could do the same operations, addition, multiplication, division, in any other base. So we're doing a review of those rules. Starting with sum, First of all, you want to align the numbers in the same position. Notice how I align them, having the same digits, like the 1 with the ones, the 2 with the twos, the fours, the eights, and the 16. Remember that these are powers of 10. That's what I in powers of 10. Now, the first step is going to be, we're going to add on the right side, 1 plus 1. This is actually 2. But 2 in binary is 1, 0, because you need a 0 on the 1. If you put a 1 on the place of the 2, that counts as 1, 2. And so you take the number on the units, the 0, you write it down under the column, and you carry the 1. I'm going to write it here. So we carry a 1. There we go. And then I move on to the next one, which would be the next column. Remember that I had a 1. It kind of disappeared, my 1. So that one that let me put it back in there. So that one, 0 plus 0 plus 1. Any base, so we don't need to make no conversion. 1 is equal to 1 no matter the base. So we move on to the next column. Now we have 0 plus 1. Again, since we got a 1, we just put the 1 digit below, move on to the next column. Now we have 1 plus 1, which is 2. 2 in binary is 1, 0. So we write down the 0, carry the 1 onto the next column. So on the very last column, we're going to do 1 plus 0 plus 1. Remember that there's 2 1s. I put them in maybe in a weird order here, but it is the 1 that I carry, the 1 below, and the 0. So you have 1 plus 1 plus 0. And that actually gives you, again, 2. So, which in binary is 1, 0. Now, I know this is confusing. Often in the book, anytime that we write down a number in a different base, we try to emphasize it. It is a good recommendation so you don't get lost. Because maybe you're looking at my operations and you're thinking 1 plus 1 cannot be 10. And so often we put like the base as a subindex. So you put a 0 and carry a 1 into the next place. But of course, there's no more digits. So that last one, you can just bring it down, you can carry it down. Or you could include imaginary zeros and just add that. So at the end, we're going to add that extra 1, that final carry. So my addition, if I add these two numbers in base 2, this is what my answer is going to be. It'll be 100,110 in base 2. So let's move on to the next one. In example 2, now I have find 32 base 4, and well, I should say 32 in base 4 plus, now this was supposed to be a sum, plus, I guess the whole statement should have been like find the sum of 32 and 12 in base 4. But I should not call them 32. I should just say 32. It's only called 32 if it's in base 10. Because the moment you're saying 30, you're saying that you have a 3 on the place of the tens. Okay, I mean, if you do call it like that, just remember it's not a regular 32. So the answer is not going to be the same. Now here, I actually put the answer by mistake, but I'm going to go through the steps. So first of all, align the numbers. These are in base 4, 3, 2, 1, 2. You want to match the place values, like units. So this is the place of the 1s, and this is the place of the 4s, because now it's increasing in powers of 4. So the base 4 starts with a 1, and then 4 squared, which is 16, and then 64, and so on. Okay, so to do this operation, like before, start on the rightmost column, the one of the units or the one of the ones. And if you add 2 plus 2, that's actually 4. But 4 in base 4 is actually 1, 0. Just like 2 in base 2 is 1, 0. Actually, any number on its own base is going to be 1, 0. So you write down the 0, which is the place of the ones, and you carry the 1 into the next place value. And so for the next column, you're going to add 3 plus 1 plus the 1 that I carry. Remember that I carry a 1. And this time I get 5. So on my side, on the side, I'm kind of like doing operations of regular numbers, and then I have to make the conversion later on. If you notice, there's that little process there. I add them like in a regular way, and then I convert them. So converting 5 into base 4, that's actually 1, 1. And again, the explanation is pretty simple, because if you have a 1 and a 4, 1 plus 4 actually adds to 5. So now you carry the 1 of the units. I'm sorry, you write down that 1 and you carry the other 1 onto the next place. But since there's nothing, you can just bring it down. So my last step is gonna what I'm calling the final carry, and this is when you bring down that final value. So the sum of 3, 2 and 1, 2 in base 4 is 1, 1, 0 in base 4. Whatever that number is. If you want to check your results, you could always convert these numbers into base 10 and then convert your final answer, and it's supposed to match. I didn't do the conversions because I want to focus simply on doing the operations in the same base. Let's move on to the next example. So now when we do sums, you can actually sum more than 2 numbers, and the same works for any base. You can add as many as you want. You can add 3, 4, 5. You just have a column of numbers stacked one below the next or one on top of the next. And so that's actually going to be my first step here. And again, I accidentally put the answer at the end. But the first step is simply to write down all of the numbers matching in vertical align them vertically like a regular sum operation, and match the units. So match 5, 6, and 4 all in the same column, and then 3, 4, and 6 all in the same column. So to find the answer, so that we always start on the place on the rightmost column, the one of the column of the ones or the units. If you add the digits 5, 6, 4, and 1, this actually gives you 15. But something that is not visible in my PowerPoint presentations, which probably is at the end, but it's not displayed, is that when you are in a base, you can only use specific digits, which are all of the digits below that base. So in base 7, I'm only allowed to use the digits 0, 1, 2, 3, 4, 5, and below the base, so the last one is 6. 7 is not allowed anymore. That's why I mentioned before, like any number like 7, it's gonna be 1, 0 on base 7. Because you need a 7 and a 1 and 0 ones. So with that number, you now use 2 digits to represent or more all of the rest of the numbers. So when I do 15, I know that I cannot write these because first of all, it has 2 digits, but it's not in the appropriate base yet. So I gotta make the conversion. 15 is the answer in base 10, but I need to convert it to base 7. So how do we convert it to base 7? Well, how many times that 7 fits into 15? Well, if twice, and then there's a remainder of 1. So that implies that 15 in base 7 is actually 2, 1. Because I need 2 7s and 1 1. So I write down the 1, and then I carry the 2 onto the next column. So on the next column now, let me put the 2 again. Now I'm gonna add 3 plus 4 plus 2 plus the 2 that I carry, and if I do this sum in the regular, that would be 11, just regular addition. But then I gotta convert 11 to base 7, and since the 7 fits 1 and there's a remainder of 4, then 11 on base 7 is actually 1, 4, because we need 1, 7 and 4 ones. And so we write down the 4 this time, which is this one, and then we carry the 1 on the next place value. As you add this actually now, since there's nothing on, there's no more numbers, it's like if you have zeros. So that's the final carry, which gives you a simple 1. So you end up getting a 1 right here. So the final answer is 141. So adding these 3 numbers in base 7 yields as a result 141 in base 7. Remember that I'm not calling them 35 or 46 or 24, and I'm not saying that the answer is 141, because since these numbers are in different bases, they represent different values if I were to put them in typical base 10. Let's move on to the next example. So now I'm gonna add a larger base. Base 16 is actually a very important base because this is used in computer science. Computer science usually use binary and what they call hexadecimal, which is very common. Even in all rockets, hexadecimal was applied. So these are like languages that the computer uses to do the processes to function. So base 16 is actually one of the important bases, even though we don't use it quite often. And the interesting thing about base 16 is that it usually has any base that is greater than 10, like base 11, 12, 13, 14, 15, 16, they start using letters to represent, because we wanted to have like one symbol, just like how we have digits. So if you notice below, it says, recall the digits in base 16. I think this probably is in my next presentation. So the first thing would be align them, just like I've been doing it before. So this number is AC4, base 16. And then the next one is 6E8, base 16. And I know they look pretty weird, huh? Like combining, but it's pretty simple. Let me show you. That's why it says recall that in base 16, these are the digits. So you have 1 through 9, that's 10. And then you also have letters, A, B, C, D, E, F. And each letter has a value, which just is the natural value. So A would be 10. B would be 11. So kind of like the corresponding value if I were to continue writing numbers. And F is 15. So you have digits 0 to 15. But to represent 10, 11, 12, I gotta use letters. So my first step, as always, is gonna be add the digits on the rightmost. So this is 4 plus 8, which is 12 in regular numbers. And then you convert it to base 16. Now, according to the digits, 12 in base 16 is C. So there's not much of a conversion, but just use the symbol that represents 12. And then I move on to the next column. In the next column, I have C and E. Well, to add them, I need to return them to base 10. So C represents 12. E represents 14. And if you add 12 plus 14, this is 26. And now I gotta convert 26 to base 16. And remember that this is kind of a division. How many times does 16 fits into 26? Well, only 1, and there's a remainder of 10. So this means that 26, you can write it as whatever digit, well, the 1 goes on the place of the 16s. And then in the place of the units, I need the symbol that represents 10, which is an A. Which is why I I write down the A on the column, and then I carry a 1 onto the next column. And so I move on to the next step. Now I'm gonna add A plus 6 plus the 1 that I had carried. That's why there's that extra 1. And to do the sum in base 10, I write the 8 as a 10. So it's 10 plus 6 plus 1. This is 17. Now convert 17 into base 16. This is not too bad. 16 only fits once, and there's a remainder of 1. So 17 is actually 1, 1 in base 16. So I write down the 1 on the place of the units. So in the same column or under the column, I write down the 1 of the units, and the next place value, which is also another 1, I carried it onto the next column or the next place value. And since there's no more numbers, then I just do a final carry, and my answer is 1, 1 AC. So if I add these two numbers in base 16, this is what I would have get. Like, this is the result that I obtained, 1, 1 AC in base 16. Okay, well, just to have the same way that I've been doing additions, I can also do subtractions in any base. So this is an example in base 9. So first of all, I need to align the numbers. And then I'm going to do the typical subtraction. I have my minus, which is subtract the bottom one from the top one. So it'll be 3, subtract 3 from 5. That's where I'm going to start. Recall that in base 9, the digits are 0, 1, 2, 3, 4, 5, 6, 7, and 8. I cannot write anything beyond that digit. As I mentioned, start with the subtraction. 5 minus 3 is going to be 2, so you write down a 2. The next one, we actually have a problem because 6 is smaller than 8. So if I subtract, that's kind of impossible. How can you subtract 8 from 6? There's not enough. In those cases, we actually borrow from the neighbor. So from the next place value, you borrow 1 unit. Borrowing a unit actually depends on the base. So usually if you were doing this like a regular subtraction, you're supposed to add 10 to the 16 because the base is 10. But if you borrow 1 from the 3, it becomes a 2. And since we are in base 9, you're supposed to add 9. So borrowing 1 from the next place value and adding it into the 6 is equivalent to adding 9. So that makes it bigger because 9 plus 6, that's going to be 15. That's going to be 15. Now I can take away 8, which the result is 7. So I write down the 7. And then I move on to the next column. Since we borrow 1 place value, then it became a 2, and 2 minus 1, that's just going to be 1. So my final answer is going to be 172. So if you subtract these two numbers in base 9, the answer is 172 in base 9. Let's do another example. Now I have base 12. So the first step is always align them vertically, matching the place values. Then you subtract. Now, before I get into the subtraction, recall that in base 12, you have digits 0 through 9 and A and B, where A represents 10 and B is 11. So when I do the first subtraction, A minus 7, that's equivalent to 10 minus 7, which is 3, so I write down a 3. Again, on the next column, I encountered the same problem, where 3 is smaller than 6. So I need to do the whole process again of borrowing 1 from the next place value. It becomes a 7. And since I'm on base 12, I add 12 to the 3. So 12 plus 3, that's going to be 15. minus 6, that'll make it 9. So I write down this 9 in this column, and I move on to the next column. Well, since I borrow 1, this becomes a 7. So now it's 7 minus 4, which is 3. So my final result would be 393 base 12. So subtracting these three numbers in base 12 gives me 393 base 12. Let's look at the next example. So in the next example, now I'm going to do multiplications. Just like how I added and subtracted, we can also do any operation. So the next one is multiplication. And the usual step is set it up in vertical alignment. I do like to do it kind of like the old ways. And usually you put the number that has the most digits, which is the 213 on top, and then the number that has less digits below. And what I'm going to do is I'm going to multiply each digit by 2. So each of the digits of the top number, I'm going to multiply it by 2. And so a reminder that when you're in base 4, the digits are 0, 1, 2, 3. So I cannot write down any digit larger than that. Well, I'm going to start with the rightmost digit on the top, which is the 3. So I'm multiplying 2 times 3, and that is 6. But because I'm on base 4, I cannot write a 6, so I got to convert it in base 4. And the 4 fits 1 into 6, and there's a remainder of 2. So 6 is equivalent to 1, 2 in base 4. And what you're supposed to do is that you write down the 2, which is the place of the units. That is actually these 2 that I already put in there. And I carry a 1, which is going to be added after I multiply. So remember that we have that extra 1. So in my next step, I'm going to multiply now 2 times 1, which is 2. But remember that I had a 1 that I carried. So 2 plus 1 will give me 3. And since 3 it's one of the acceptable digits, then I just place it to the left of the 2. I write down a 3. Now I move on to multiply the last digit. So my last digit is 2 times 2, which is 4. And 4 in base 4 is 1, 0. And so I write down the 0, which is the place of the units or the ones. And I carry the place value as a +1. But since there's nothing else to multiply, you could even, if you want to, you could do that thing where you add zeros, and you could say like 2 times 0 is 0 plus 1 is 1. So you put a 1 at the end. Or simply, many people like to say, since there's nothing else, then just bring that 1 down, which is also sometimes called the final carry. You carry down that 1. So the result is 1032. So if you multiply 2 times 213 in base 4, the result is 1032 in base 4. And once again, all of these operations, you can check them by converting these numbers to regular numbers, and then the result actually has to match. If you multiply those in base 10, that should be equivalent to whatever this is in base 10. I'm not doing the checking, but you can check your operations. In the next example, now I have a multiplication of 2 digits with the 2 digits. This is usually how we learn to do operations when we're in elementary school. We start by doing like 1-digit multiplications, and then we have like 1 digit below and many digits on the top. And after that, you have like multiple digits, and then you do decimals. So all of that can be learned and can be performed in any base. So the next base is actually base 8. And I have 25 times 3, 4. It would have not mattered if I had put it in a different way. And actually, my preference is always to have, if there's a number that has more digits than the other one, I like to have it on top. But in this case, it would not matter if you have written 3, 4 times 2, 5. Because remember that multiplication is one of those operations that the order doesn't matter. The result is always like, we usually like to say the order of the factors do not alter or do not change the product at the end. Well, let's start it. Before I begin multiplying, reminder that the digits in base 8 are 0 through 7. I need to use one of these digits. And start by multiplying. So I'm going to start by multiply by the right digit, which is 4. So I'm going to do the kind of like how I did it before. I'm going to start by multiplying all of the digits on the top by 4. And then I'll move on to the next one, which is 3. So you multiply 4 times 5, that's actually 20 in base 10. But we got to convert it to base 8. So A fits twice into 20. And then the remainder is 4. So that means that 20 is 2, 4 in base 8. So I write down the 4, which I have it here, and I carry the 2 onto the as a sum for the next value. So in my next step, I multiply now 4 times 2, which is 8, plus the 2 that I carry, so that's 10. Then I gotta 10 into base 8. 10 in base 8 is actually 1, 2, because the A fits once and there's a remainder of 2. So 10 is 1, 2 in base 8. And that's what I can do the same thing, write down the 2, which is that one, and carry the 1 onto the next value as a plus, as an addition. But since there's nothing to multiply, I just do the final carry, and I get 1, 2, 4. So my multiplication of 2, 5, if you multiply 2, 5 by 4, my result is 1, 2, 4. Now I move on to multiplying now by 3. So I start on the right. We want to do it in order. 3 times 5, that's going to be 15 in base 10. In base, if you convert it to base 8, it becomes 1, 7, because the 8 fits once and there's a remainder of 7. And so you write down the 7. Now notice how I did not start it under the 4. We leave a gap in there, or sometimes people add 0. The reason for that is because since this 3 is on the left place, this 3 is not a unit. So whatever result you get it on the second place. So you start on the second place. So I put the 7 and I carry the 1 to be added to the next multiplication. Well, the next multiplication is 3 times 2, which is 6, plus the 1 that I carry, that's going to be 7. So here, 3 times 2 is 6, plus the 1 that I carry, it gives me 7. And 7 is an acceptable digit in base 8, so I just put it down. There's nothing to carry. And once you have these numbers, you're supposed to add them. So the sum is going to be, now you do a sum in base 8. So like I mentioned, you could put a 0 in here, because if you were to add 1, 2, 4 and 7, 7, you should have aligned them. But because of the placement of the 3, the result actually has a 0 in here. And that's the real reason why we do multiplications like this, why we add it, because we take into account the place value where the digit is located. If I actually had more digits, I would continue leaving or adding more zeros. It would be 4 plus 0, which is 4, and then 2 plus 7, which is 9, but I gotta convert it to base 8, and 9 is equal to 1, 1, because to get a 9, you need 1, 8 and 1, 1. So I put a 1 and I carry a 1. And then 1 plus 1 plus 7 gives me 9. So I keep doing the same thing. I put a 1 and I carry the 1 on the next digit, but there's nothing else. So I just do the final carry. So the sum of 124 and 770 is 1114, which is my final answer. So this is very interesting that when you're doing multiplication of more than one digit, you're doing both operations at the same time. You're multiplying and you're adding. And this is the regular way that we do it. Also, if you were wondering, like, why do we always leave spaces? Is because of we take into account the place value. So regularly, not regularly, but literally these numbers, actually, it's not 77, but it's 770. There's a 0 on that place value. Okay, let's move on to another example. On the next example, I'm actually going to do divisions. And division, just like with multiplication, the interesting thing about it is that you're multiplying and subtracting. So you're doing the other operations as well. It's not just like the one operation. I like to do division the old-fashioned way. We call this number the dividend, and this is the divisor. So I'm going to divide 324 by 3. So I could also read it as how many times does 3 in base 5 fits into 324 in base 5. And so I set it up already. Usually the dividend is what goes inside of the division symbol. This is my division symbol. And then the divisor goes outside. And notice, since we are in base 5, that the only digits, my final answer has to have these digits, 0, 1, 2, 3. And all through my operations, I can only use those digits. I cannot use anything bigger than 4. Well, you might have noticed I kind of already hinted what I'm going to do because I put a comma. And the way that we always teach this is that you take as many digits as the number that is outside. Since the number outside is a 3, then you start on the left and you separate the first digit. And then you ask yourself, how many times does 3 fits into 3? Well, of course, that fits once. And then you multiply. So now you do like 3 times 1, which is 3, and you subtract. This 3 minus the 3 below, that is 0. The remainder is 0. After finishing down, you automatically bring down the next or carry down the next digit. So you end up getting a 2. And you ask the question, how many times does, now 0, 2, putting zeros to the left does not increase the number. That's just 2. So how many times does 3 fits into 2? Well, none, because 3 is bigger. So that's going to be my next step. In those cases, we add a 0 on the top, and then we bring down the next digit. So I bring down the 4. So by adding this 0 on the top, it allows me to bring down one more digit. So that 2 becomes now a 20. Well, not necessarily a 24, my mistake. So it becomes 24, whatever that is in base 5. So to guess what goes on the top, I cannot do the regular division or the regular multiplication. I have to do them in base 5. So to guess what's going to be the next digit, what I'm going to do is, and this is the way that we usually divide, is that you look at all of the factors. What is the largest factor of 3 that would fit into 2, 4? Well, how would I know? We'll do all of the multiplications. 3 times 1, that's just 3. 3 times 2 is 6, but in base 5, that is 1, 1. 3 times 3, that is 1, 4, because it's 9, and in base 5 is 1, 4. 3 times 4 is 12, and in base 5, that is 2, 2, and that's already pretty close. If you were to do one more, I didn't, but that would be larger than 2, 4. Because if you multiply 3 times 5, that is 15, and in base 5, that is 30. So this one already is too big. The number that is it's less, is smaller than 2, 4 would be 2, 2. So that means that if it's 4 times, so I put the 4 on the top, I multiply them 3 times 4, which in base 5 is 2, 2, and then I subtract them. So that's going to be my next step. And the subtraction, of course, this subtraction is in base 5, but because all of these digits are less than 5, then you just subtract like the regular way. 4 minus 2 is 2, 2 minus 2 is 0, so the remainder is 2. And I pretty much stop there because 3 does not fit into 2 anymore, and there's no more digits to the right to continue bringing down, so I finish. I end once there's no more digits to bring down. So we can say that if you divide 3 to 4 in base 5 by 3 in base 5, the result is 104 in base 5 with a remainder of 2. So the result is 14, but there's a remainder. So it doesn't fit evenly. It leaves a remainder. When a number divides evenly or fits evenly, you're supposed to have a remainder of 0. Let's move on to the next example. So now I'm going to divide 2 digits. So this is 111001112 base 2 divided by 10 in base 2. So let's do the setup. Write down. Now you might have noticed that I color some of these digits just to make it easier to track which digit is which. And I mentioned it before. Separate the same amount of digits that you have outside. So I like to separate them by putting a comma. And then I ask myself that how many times does 10 fits into 11? Well, one might realize they only have like one unit, because if you add 10 plus 1, that would give you 11. So they're pretty close. It fits ones, and there's a remainder of 1. So that one, we don't really need to like do the multiplication tables to estimate what is the largest number. We can see the largest number that fits is 1, and the remainder is 1. So now you bring down the next digit. So you end up getting again 1, 1. And just like before, if it's 1, so you put a 1 on the top, then you multiply 10 times that 1, which is, well, it's not really 10. 1, 0. So you multiply by 1, it gives you the same thing. And then you subtract 1, 1 minus 1, 0, pretty much the same operation, which is simply 1. Okay, so now you bring down the next digit, which is this 0, and it becomes 10. It becomes 1, 0. And 1, 0, since I'm dividing exactly by the same thing, if it's ones. And now this time the remainder is going to be 0. But now you bring down the next digit, which is now the green 0. And because this is 0, 0, and this is larger, it does not fit into it. It's too small. So in those cases, we put a 0, which I put it in green, and then I carry down the next digit. It becomes a 1. Well, even though I have zeros on the left, 0, 0, 1 is still a 1. Have you ever heard? There was a saying where they used to say like zeros to the left do not change anything. So these zeros to the left do not matter. That's just a 1. And so this number is too big because this is a number of 2 digits that's not going to fit into a number of 1 digit. So I need to put another 0 and bring down the last digit, which is the 1. And it gives me 1, 1. And I've done this division before if it's ones. And the remainder is 1. So if you divide all of this by that, the result is 111,001, which is all of this, base 2, and I have a remainder of 1. So it doesn't fit evenly. Okay, so to conclude today's lesson, I am going to talk about prime numbers. A prime number. Before I get into prime numbers, a quick review of what a divisor or a factor is. If you have a number A, a divisor or a factor, well, actually A is going to be my divisor or factor of another number B if or provided that there exists a number J such that A times J equals B. This is actually the formal definition of division. Typically, when we think of factors, we think more about division. Like we would say 2 is a factor of 5 because, actually of 6, because you can divide 6 by 2, and it fits evenly, and there's a remainder of 0. But the official definition is actually made as a multiplication, where the reason, and that's why we can use these two words. It's not that it's wrong, but it's usually more complicated to work with divisions. So an equivalent way of looking at divisors is by looking at factors. And in that sense, we're thinking about it as multiplications, but it's the same thing. We're just saying that you can write 6 as 2 times another number. And of course, the division actually shows us that that number is 3. So 2 and 3 are both factors because they appear as members or like terms in the multiplication of 6. So anytime that you can use a number to represent another one as a multiplication, those are factors or divisors. Maybe let me give you another example. 25, a factor is 5 because 5 times 5 is 25. 144, a factor is 12 because 12 times 12 is 144. They don't need to be the same one. If I were to do maybe 56, 7 and 8 are factors because 7 times 8 is 56. Okay. So one of the questions is, can you find all of the divisors or all of the factors of a number? And yes, there's actually formulas how to do it, but you could do it one by one. For example, if I focus on 9, what are the divisors? What are the numbers that divide it? Well, remember that 1 divides every number. So it's divisible by 1. It's also divisible by 3 because 9 is equal to 3 times 3. And it's also divisible by itself because every number is divisible by 1 and by itself. So it has 3 divisors. The next example is 11. 11 is actually a special number because you can only divide it evenly by 1 and by 11. And remember that when I say evenly, I mean that the remainder is 0. If I try to divide 11 by any other number less than itself, let's say 5, if it's twice, but there's a remainder of 1. So it doesn't really divide it evenly. It doesn't really split it into even parts. So the only divisors are, that's why we introduced that multiplication, because when you look at, it would seem that you can always divide any number by any number, but it's not evenly divisible. When you think about multiplications, it should be obvious that you cannot write down 11 as 5 times another number. Okay, so the next one, 24. This number has a lot of divisors because it's a little bit bigger than the other ones. So it's divisible by 1. It's divisible by 2 because 24 equals 2 times 12. That also means that 12 also divides 24. It's also divisible by 3 because 24 equals 3 times 8. That means that also 8 is a divisor. And it's also divisible by 4 because 4 times 6 divide. 4 times 6 is 24, so they're both divisors or factors. So this has a lot of them. 1, 2, 3, 4, 5, 6, 7, 8. So 24 has 8 natural divisors. Remember that natural numbers are supposed to be greater than 1. So we don't take into account 0 and we don't take into account negatives. And any number that is bigger than it would not fit into it. Okay, after that, now we can talk about prime numbers. A prime number is a natural number greater than 1 that has exactly 2 factors or 2 divisors, itself, so the whole number, and 1. So it has exactly 2 factors or 2 divisors, no more, no less. A composite number is a natural number greater than 1 that is not a prime number. So those numbers that don't have exactly 2 divisors will be called that have more than 2, that have 3, 4, 5, 6, 7, any amount bigger than 2. They're gonna be composite numbers. Examples of these prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and the list actually goes on. There's infinitely many prime numbers. Similarly, the composite numbers are the other numbers that I did not take into account, such as 4, 6, 8, 9, 10, 12. Notice that 1 is not considered neither prime nor composite, because by definition, any prime number has to be greater than 1, and also any composite number has to be. So 1 is neither prime nor composite. Sometimes we call it the unity, not the unit, the unit. So it's like its own number in itself. In fact, the definition of prime would say that has 2 divisors, but 1, if you divide it by 1 and by itself, it's just that 1 number. Okay, so what we're interested in this section is to create or to do to determine if a number is prime or composite. So I have 3 examples. 47 is actually divisible by 1 and by itself. How would I know? Well, you have to try dividing it by other numbers. You have to try dividing it by 2, by 3, by 5, by 6, by 7. And you realize that none of them fits evenly into 47. So, or in another way, you cannot write down 47 as a multiplication of any of these numbers times another number. Not if they're natural numbers. Natural numbers do not take into account decimals. The next number, 171, is actually not a prime because it has more than 2 divisors. It's divisible by 1, by 3, by 9, by 19. So therefore, this is composite. The last one is 91. And 91 also, it's well, actually, 91, it says priming here, but it should say composite because it is divisible by 7 and by 13. In fact, if you multiply 7 times 13, that's 91. So it has 4 divisors, 1, 7, 13, and itself. So this is composite. The only prime was 47. So obviously, like, one of the challenges is how can I determine if it's a prime without having to do the whole division? Is there like a quick rule to know if the number is divisible by another number? And the answer is yes. We call this the divisibility test. I'm not gonna go over them because I'm almost at the end of the presentation, but this should be on your book. And these are like quick rules. For example, to know if a number is divisible by 2, the number, it has to be an even number. So even numbers are always divisible by 2. For example, 846 is considered even, so it's divisible by 2. And like that, we have like rules to determine divisibility by any of the numbers, by 3, by 4, by 5, 6, 8, 9, 10, 11, and so on. If you can't find this on your textbook, you could Google these things and you'll find them for sure. These are very popular. And you might have already heard of some of this. Now, in this part, I wanted to give you an example of how to check divisibility. So I had like a large number, and then I wanted to check if it's divisible by 3, by 4, by 10, and by 11, applying those rules. I'm only gonna do one of them, which is the 3. So the rule says that a number is divisible by 3 if the sum of its digits is divisible by 3. So if I look at all of the digits, 3, 4, 1, 5, 6, 5, and I add them, that gives me 24. And 24 is actually divisible by 3 because 24 equals 8 times 3. So since the sum of the digits is divisible by 3, the entire number itself is also divisible by 3. I'm not going to go over the other 3. I'm not going to show you the divisibility test for 4, 10, or 11. But they're not very difficult. Like I said, they're on the book. And it actually turns out that this large number is only divisible by 3. It's not divisible by 4, not by 10, not by 11. Okay, this is the last thing that I want to talk about, the prime factorization. So the prime factorization is very, very important because we use it to solve a lot of problems. Even when you go to a math competition, often you can solve a problem by looking at the prime factorization. We also call these the building numbers. And the idea, which is the fundamental theorem of arithmetic, is that every composite number can be written as a unique product, as a unique multiplication of prime numbers. That's what we call it, the building. The primes are kind of like the building blocks because you can use it to construct any other number. And so this is the very, very last thing. It says determine the prime factorization of the following numbers. In A, I have 315. So I want to write it as a multiplication of using only prime numbers. Well, you could start with the smallest one. It's not divisible by 2, but then the next one would be 3. 315 is divisible by 3, and you get 105. And then you continue dividing by 3. This is divisible by 3, and you get 35. And 35 is not divisible by 3, but 35 is divisible by 5, is equal to 5 times 7. So these factors, it's my prime. Each of these are prime numbers. So 315 is equal to 3 squared because I had 2 3s, 1 5, and 1 7. And this prime factorization, you can get to it in different ways. It doesn't have to be like in a particular way. If you would have started by dividing it by 9, you get 35. And then you kind of divide each one of them or split each one of them. 9 is 3 times 3, and 35 is 5 times 7. And still gives you the same factors that I found on the other factorization. And in a similar way, you can factor 273. You can write it as a multiplication of prime numbers. And similarly, you can write down
Thank you, Mr. Tintos, for your presentation and for all the information. And thank you to all who attended today. I wanted to go ahead and show you our schedule for next week. Actually, no, for the following week, because we are going to be on spring break. So the next session will be on Friday, March 27th. We will have Happy Math Hour, Math 1332, which will be Exam 3 review, along with Math 2412, sequences, series, and mathematical induction, as well as our student success topic, which is on credit card debt. Please stick around, though, this Friday on the 13th for our student success topics, counseling with Oscar Velasquez. We hope to see you all. Have a lovely spring break and good luck on all your exams. Thank you, everyone. Have a good rest of your day.